an ASIC is designed using pre-designed logic gates. And the pre-designed logic gates used for designing an ASIC are organized into what we call a standard cell library. A standard cell library may contain hundreds of logic gates, such as AND gates, OR gates, NAND, NOR, flip-flops, XORs, etc. Even some complex functions such as half adders, full adders, or even more complex functions can be part of a standard cell library. A standard cell library is developed for a particular foundry and process node. Foundries, the foundries that we have in the world today, the big ones are TSMC, which is a company that's based in Taiwan, and Global Foundries, which is a American company with manufacturing facilities around the globe. Samsung in Korea, UMC. So these are some of the names of foundries that exist today. And foundries are essentially the factories where chips are manufactured. So for a particular, in any given foundry, you would have multiple process nodes. And these are usually denoted by the minimum transistor length. So you could have a 40 nanometer, you have 40 nanometer, 28 nanometer, 16, 7, 5 nanometer, etc. These are the different process nodes that you may find in these different foundries. So for any combination of foundry and process node, let's say TSMC 28 nanometers or Global Foundries 7 nanometers, in any such combination of, for any such combination of foundry and process node, you will have a specific standard cell library. And that standard cell library can only be used if the chip is being manufactured in that foundry with that process node. If that foundry, in that same foundry, if the chip is going to be manufactured in some other process node, then a different standard cell library would have to be used in designing that ASIC. The cells in a library. A standard cell library will contain cells for a wide variety of logic functions. So you would have a variety of combination functions, as I said, NAND, NOR, MUX, adders, etc., etc. Then there will also be various sequential functions. Usually they're all different flavors of a D flip-flop. So you could have a normal D flip-flop. I'm just calling it DFF for D flip-flop. You could have a D flip-flop with reset, so it's DFFR, a D flip-flop with set, so DFFS. So let's say a negative edge-triggered D flip-flop. You know, D flip-flops are edge-triggered devices, so they trigger at the active edge of a clock. The active edge of the clock may be the rising edge or the falling edge. So you could have two different types of D flip-flops in the library for those two cases, and so on. So you can have all these varieties of sequential cells, usually different flavors of D flip-flops. Some libraries may even have multi-bit flip-flops, where you have a flip-flop with with 2, 4, or 8 bits it can store. Libraries differ, and they come from different vendors, and they may have different numbers of cells. Libraries will also typically have level-sensitive latches. Then for any given logic function, let's say a 2-input NAND, there may be many cells. So each of the cells is for the same logic function. Let's say a 2-input NAND. But what differs? What differs is that these cells will have different, what we call drive strengths. The drive strength of a cell can be changed by changing the following properties of the PMOS and NMOS transistors in the cell circuit. So the width of the PMOS and NMOS transistor, the length, and the threshold voltage. So in a library, for a given logic function, let's say a 2-input NAND gate, you could have maybe 6, 7, 8 different 2-input NAND gates in a library. And those 6, 7, 8 different NAND gates would only differ not in the functionality. They are all 2-input NAND gates. They all have the same function, but they will differ in their drive strength. And the way that difference is created is by designing those different cells with different transistor widths or different transistor lengths, or with different transistor types, meaning the transistors with different threshold voltages. This is an illustration of the drive strengths of cells, just to drive home the point. It is, the fact that standard cell libraries have cells with different drive strengths is critical to the use of a standard cell library. In fact, without having a variety of drive strengths in a standard cell library, you will simply not be able to design an ASIC that meets timing. You would only be able to design an ASIC that meets the functional requirements, but it will not be able to meet timing requirements unless you do have a variety of drive strengths. Also, without a variety of drive strengths, the implementation of the logic can be very non-optimal. The logic, the area of the standard of the library may be too big, or it may consume too much power if you don't have different drive strength cells in the library. So what is the meaning really of different drive strength? So as drive strength increases, the cell can switch its output faster. That's the key. That's the key thing for drive strength. The reason we have different drive strengths is that the timing characteristics of the gate changes as the drive strength changes. The functionality remains the same. The timing properties change. So I'm trying to illustrate that with this diagram here. You can see that I have 3 2-input NAND gates shown in these 3 different circuits. And those 3 different NAND gates are all driving the same OR gate. Okay, so imagine you have a NAND gate driving an OR gate. In the first instance here, I have a NAND 2 of drive strength X1. And then I have a NAND 2 of drive strength X2 and a NAND 2 of drive strength X4. Okay, so 3 different drive strengths, increasing drive strength. All these 3 NAND gates are driving the same OR gate, and the wire connecting the output of the NAND gate to the input of the OR gate, let's assume that wire is the same length. Okay, so you can imagine that all these 3 NAND gates are driving the same capacitance, the same capacitive load. And now look at the inputs of these 3 NAND gates, which is shown in blue here, and I'm showing the same input waveform for all the 3 NAND gates. So that blue waveform, which is the input waveform, has the same transition time in all the 3 cases. It's going from high to low, and the time it takes to go from high to low is the same. Okay, the output of the NAND gate is a red waveform, and that's where you see the impact of the drive strength. So if you see NAND to X1 drive strength, the gate takes longer to go from low to high in response to the change in input. And as the drive strength increases, the transition time at the output decreases. The output switches much faster. It goes from low to high much faster. So that's one key aspect of change in drive strength. The other thing that is not apparent in the drawing is the delay from input to output. So when the input transitions, how much later will the output transition? That delay also is drive strength dependent. And as the drive strength increases, the delay decreases. The output responds much sooner to the change in input. Okay, so greater the drive strength, the faster is the gate. It switches faster and it takes less delay to switch. The flip side of an increase in drive strength is that as drive strength increases, the cell becomes larger, it takes more area, and it dissipates more power. Okay, and whenever we design an ASIC, we want to design an ASIC with a minimum area, because as the area increases, the cost of the ASIC will increase. And the cost is a very sensitive function of area. So as the area increases, cost increases very quickly. In fact, it may be non-linearly increasing. So there's a lot of interest in designing ASICs to design them with the minimum area. And the problem with, so even though even though higher drive strength cells can operate with at higher speed, the problem is that they also will give you more area and therefore drive up costs. Also, the higher drive strength cells will consume more power because the transistors are wider, so there will be more current flowing through those high drive strength gates, and therefore more power is dissipated. In general, the idea in designing ASICs is that for a given logic function, for whatever functionality you're designing, for whatever is the timing requirements that you have to meet, the designer should use the smallest drive strength cell needed to meet the timing requirement.